So in last class, am I audible?
Yes,
Hello.
yes, sir.
Yes.
Okay. So in last class, we have solved the tube flow problem by using for the Bingham fluid model. है ना? Today we will solve the falling film problem for the Bingham fluid. So this is the last problem related to the non-Newtonian fluid. After that, we will start the new chapter. Okay, so this is the last problem. So basically, you have already solved the falling film problem for Newtonian fluid and the power law fluids. So basically, you have a slope where a fluid is falling due to the gravity, really falling due to the gravity. There are no other forces applied on the fluid, only the gravity is applied on the fluid. The angle of the slope between the to the vertical angle is the beta. The thickness of the film is the delta.
सर स्क्रीन नहीं दिख रही जो आप लिख रहे हो वो वाली.
Okay, एक मिनट रुको. अब विजिबल है?
Yes, sir.
Okay. So you have already solved this problem before for the Newtonian fluids and the power law fluids. A fluid is flowing on a tilted or the tilted slope due to the gravity. Okay, inclined slope due to the gravity. The angle of the inclined slope is the beta. The thickness of the liquid film is delta. Only the gravity force is applied on the film, and you have to substitute the axis. So it is a Cartesian coordinate system we can use. This is the x-axis. This is the y-axis. The length of the slope is L. Okay, now you have to develop the correlation for the Bingham fluid. Okay, so as we had solved for the last problem, it will move in the two different ways. Okay, so when the Bingham fluid will flow on a surface, so there will be two different layers. Okay, at the one layer, these are the two different layers inside the fluid. Okay, so in this layer, fluid behave like a liquid. Okay, and in the above layer and the upper layer, fluid behaves like a solid material. So if you plot the velocity profile, you will find that at the upper layer the velocity is constant, because the shear stress value will be lower. Okay, at the lower layer the velocity will reduce like the Newtonian fluid. So suppose this thickness is delta naught. Now you have to solve the problem. You have to develop the correlation for the velocity profile. So initial stages will be same. First you have to determine the non-zero velocity, which is v. This is the z-axis. This is not y-axis. This is the z-axis. So the velocity is vz, which will depend upon x. So the shear stress component is tau xz. That is the non-zero shear stress component. Now you can directly use the equation of motion from the table. So this is the equation of motion for Cartesian coordinate system. These are for the Cartesian coordinate system. You have to just take the table and calculate the non-zero components of the equation of motion. Okay, so in next page we have substituted the equation of motion. So
And ये
these are the,
cylindrical coordinates के लिए है?
okay, these are the cylindrical. Now we have to take on the, we should take the Cartesian coordinate. 1 minute. These are the Cartesian coordinate system. Okay. Now here, this is equation of motion for Cartesian coordinate system. Now you have to select the non-zero profile. So non-zero is Vz, which will depend upon x, and tau xz. Only these two components are non-zero. There is no pressure force applied there. Only the gravity force will be there. Okay. So tau z, Vz will be non-zero, and tau zx will be non-zero. In first equation, you will find all terms will be zero. In second equation also, all terms will be zero because Vy is zero and tau xy, tau yy, tau zy is zero. Pressure is equal at all sides, so you don't have any pressure difference. In third equation, right hand side, you have Vz, but Vz will not depend upon time. Vx is zero, Vy is zero, second, third term. Fourth term, Vz will not depend upon z. Vz is only depending upon x-axis. So in the these all terms are zero. Here pressure difference is not there. And it is the freely falling, not due to the pressure. It is due to the gravity only. Tau xz, this is only non-zero term. The second and third terms are zero. Gravity is there, but gravity is Gz is equal to g cos beta. Okay, because angle, slope angle is beta, so this is the g cos beta. So just take the values 1 by rho minus 1 by rho del by del x tau xz equal to g cos beta. Now solve this equation. You can easily integrate this. You will get tau xz equal to rho gx cos beta plus t1. Okay. Now if x equal to 0, then tau xz equal to known. Okay. So basically here you can use that at x equal to 0, the viscosity, the shear rate at the liquid and shear rate and at the gas, both should be equal to. And if both should be equal to, then the shear stress should be equal to, because viscosity's values are different. So we had done this thing before also. So I am again writing this, because as at x equal to 0, tau xz air, because there is a air above, equal to tau xz liquid. Now for air you can write dvz by dx. Here this is for dvz by dx for air, and liquid dvz by dx for liquid. And also this is also for liquid. This is for air, this is for liquid. Now in this equation, you know that the viscosity of liquid is far larger than the viscosity of air. So eta liquid is much greater than eta air. Okay, this is the eccentric viscosity. So eta liquid should be much greater than eta air. That means this value, this is only possible when dvz by dx should be several times less than dvz by dx air, and this shows that this value should be negligible. Okay, this shows that this value should be negligible. So tau xz should be negligible. Okay, so once this value is negligible, that means c1 equal to, at x equal to 0, this is 0, so c1 equal to 0. So you will get tau xz equal to rho gx cos beta. So till there, till this is equation number 1. So till equation number 1, your expression, your solution is same. After equation number 1, you have to use either the Newton's law if the fluid is Newtonian, if power law, if the fluid is power law, fluid obeys the power law, and the Bingham fluid model if fluid obeys the Bingham fluid model. Okay, now we will solve by using the Bingham fluid model. So for this system, Bingham fluid model may be written as first, for tau is less than tau naught or x is less than x naught, fluid flows like, or x is less than delta naught, not x naught, delta naught. Okay, so if tau is less than tau naught or x is less than delta naught, then fluid flows like a solid block. Okay, so fluid behaves like a solid block. Okay, so what I am saying that at this point, if del is less than delta naught, है ना, from here to here, or this range, it moves like a solid block, है ना, because shear stress values are less. Okay, that is lesser than the required to flow, the value of shear stress required to flow. Once the shear stress becomes gain the initial point, once the value of the shear stress is higher than the tau naught, then only fluid starts to flow. Okay, so x is less than delta naught, not tau naught, delta naught, है ना, x is less than delta naught. Okay, so at that time velocity is constant because it looks like a solid block. Or when you solve this equation, you will get vz equal to v naught, which is a constant. So you have to at the last you have to determine the value of this constant also, v naught. What is the value of v naught? Okay, now second equation is for tau is greater than or equal to tau naught, or x is greater than or equal to x naught, delta naught. You can say eta equal to mu naught plus minus tau naught divided by, in bracket, dvx by dz, bracket close. Okay, so this is the value of eta. Now you can, first you have to determine the value of del naught, because this is a condition in two phases. So what is the value of del naught? Okay, so how to calculate the value of del naught? That is also called the critical thickness. Okay, so at tau xz equal to tau naught, del x equal to del naught. So from equation number 1, you can calculate the value of del naught. Okay, so we can write the critical thickness of film del naught is unknown. So we can calculate from equation number 1, tau equal to rho gx cos beta. So at x equal to del naught, tau equal to, we can use this as a boundary condition to determine the value of del naught. Okay, so at x equal to del naught, tau equal to tau naught. So tau naught is the property of material which is given, like viscosity or density, है ना? So you know the value of tau naught, but del naught will depend upon the structure. So for solving the problem, first you will determine the value of del naught. Rho, g, cos beta, these all are the properties of the material or the system that that will be given to you. Okay, so tau naught equal to rho g del naught cos beta. So just rearrange this equation, you will get the value of del naught. Del naught equal to tau naught divided by rho g cos beta. This is equation number 1. Equation number 2. Okay, 1 is already there. This is equation number 2. Now, once you know the value of tau naught, del naught, then you can calculate, use the equation to solve the problem. Okay, so we had already solved the problem for first part at when x is less than del naught. Then you have the vz equal to v naught, which is constant. Now we have to solve the equation for the second reason. Okay, so second reason is when x is less than, when x is greater than del naught. Okay, so we will solve for the second reason. If tau is greater than or equal to tau naught and del is or x is greater than del naught, then you have eta equal to, in bracket, mu plus minus tau naught divided by, inside the mode sign, dvx by dz, mode bracket close. Okay, now you have to remove this mode sign. So once you remove the mode sign, based on the mode sign, you have to select either the plus or the minus sign. Okay, so here you can see that once you go in the positive direction of the x-axis, the velocity will decrease. Okay, so when you move in the positive direction of the x-axis, velocity will decrease. That means tau dvz by dx is, this quantity is negative. Okay, so this quantity is negative. So you have to take the negative sign after removal of the mode. So you will get eta equal to mu naught plus minus, minus naught plus mu naught minus tau naught divided by dvx by dz. Now just substitute this in the original equation. So the original equation is Okay, so we have written in the wrong place. Basically, here we have to write. So once you remove the sign, because dvx by dz is negative, eta should be equal to mu minus tau naught divided by dvx by dz. Now tau xy equal to tau xz equal to minus eta multiply by dvx by dz. Just substitute the value in the original equation, you will get eta equal to this. Just substitute here, you will get tau xz equal to mu minus mu dvx by dz plus tau naught. These two quantities will cancel out. So this is equation number 3. Equation number 3 is tau xz equal to minus mu dvx by dz, dvz by dx plus tau naught. Okay, now you have to, this is wrong. 1 minute, I just correct this. This is not dvx by dz, this is the dvz by dx. Okay, this should be dvz by dx. This is also dvz by dx, because velocity should be in the z direction. Here it is correct, here it is correct, here it is wrong. No, we have to correct here also. This should be dvz by dx. Here also this is dvz by dx. Okay, now okay, now you have to just substitute the equation number 3 in equation number 1. What is the equation number 1? Equation number 1 is this: tau xz equal to rho gx cos beta. So rho gx cos beta equal to equation number 3, that is minus mu dvz by dx plus tau naught. Okay, so just substitute this: minus mu dvz by dx plus tau naught equal to rho gx cos beta. Just rearrange this equation, you will get dvz by dx equal to minus rho g cos beta, rho g x cos beta divided by mu plus tau naught divided by mu. Okay, now you have to just integrate this, you will get vz equal to minus rho g x square cos beta divided by 2 mu plus tau naught by mu x plus c2. So c2 is the integral constant. Now you have to take the boundary conditions. So boundary condition is at x equal to delta, vz equal to 0. Just substitute the x equal to delta boundary condition. The second boundary condition, at x equal to delta, vz equal to 0. So just substitute x equal to delta, you will find vz equal to 0. So c2 equal to rho g delta square cos beta divided by 2 mu minus tau naught divided by mu delta. Okay, now substitute, this is equation number 4, this is equation number 5. Now substitute equation number 5 in 4. So you have to substitute the value of c2 from there. Okay, you will get Vz equal to rho g delta square. I'm just taking common the delta square cos beta divided by mu 2 mu in bracket 1 minus x square divided by delta square bracket close minus tau naught delta divided by mu. Here I have taken the common tau delta 1 minus x by delta. So this is the value of Vz. Okay, now if you want to calculate V naught, so at x equal to delta naught, Vz equal to V naught, just substitute the value, you will get the value of V naught. So V naught equal to rho g delta square cos beta divided by 2 mu in bracket 1 minus del naught square divided by del square minus tau naught del divided by mu in bracket 1 minus del naught by del. Okay, so these two equations, this is equation number 6 and 7. So equation number 6 and 7 represents the Bingham fluid model. Okay, so when the fluid flows in an inclined plane, on an inclined plane, so because of the lesser shear stress, the upper part moves like a solid block. Okay, and the bottom part that feels the higher shear stress due to the friction with the solid body. This is the solid surface. So the bottom part feels the higher shear stress due to the friction of the solid body that flows like a fluid. So this layer works like a lubricant. The upper layer works like a solid block. So here the velocity of the solid block is V naught. Here the velocity is V naught. At the bottom part, velocity can be represented by the equation number C. This is the V. So V can be represented by equation number 6, and V naught can be, I'm writing more, and V naught can be represented by equation number 7. Okay. Here velocity is V naught. That can be represented by equation 7. Okay, so this is the constant velocity, which is constant. Here all the quantities are constant, so V naught is a constant. V is variable because it depends upon x. Okay, so this is the Bingham fluid model. Similarly, you can use other models also. We have I have already taught you the Alice model and Ehring model, then the Filipov model and the Rankine-Filipov model. So all these models, you can use these models to design the flow patterns or the flowing channels for the respective fluids. Okay, so this is the example how to use the non-Newtonian model to design the different type of flowing channels. Okay, now whatever studied we completed till now in the fluid kinetics. Initially, the first unit was related to fluid statics, where we study how to calculate the hydrostatic force and how to develop the models for the barometer, U-tube manometers. Then we have also studied how to design the different type of decanters. Okay, so that design part comes under the fluid statics. After completing the fluid statics, in the fluid kinetics part and the fluid dynamics part, we have covered the micro scale studies. Okay, so whatever the study we covered, equation of motion, after equation of motion, design of the different types of flowing channels, which you also covered in the momentum transport, in the transport phenomena. So that is the overlap part in the momentum transport and the fluid mechanics. Then we have covered the non-Newtonian fluid and how to design the equipments for the non-Newtonian fluid. So all these parts are these equations and the theories are the part of the micro level fluid mechanics. So what is the difference between micro level fluid mechanics and the macro level fluid mechanics? So when you study the macro level fluid mechanics, basically you are trying to solve the problem for the small scale. Suppose this is the fluid flowing inside the tube. Okay. Now you want to determine what is the velocity at this particular point. So for that you need the micro level fluid mechanics. Okay. So in this differential equation here, you just substitute the value of x, you will get the value of vz. So this vz is the local velocity at this point. है ना? So from here to here, its distance is 2 meter. So after 2 meter, what is the velocity? That you can calculate from the micro level study. The limitation of micro level study, that can be easily done for the laminar flow, but if you are talking about the turbulent flow, that is very difficult. Okay, for that you need the computational software. Although the equation is same, for turbulent flow also you have to solve the equation of motion only, but the difficulty is when you use that same equation for the turbulent flow. So this is the equation of motion, and these are the equation of motion for the turbulent in the generalized form. For turbulent flow, the velocity will depend upon all three directions. So Vr is not zero, V theta is not zero, Vz is not zero, tau Rr, tau R theta, tau Rz, all will be there. So these equations will become the three equations, which is the second order differential equations. So you have to solve the three second order partial differential equations together to solve one problem, and that is the very much difficult part. Okay, because solution of the second order differential equation, that also the partial differential equation, and these differential equations are the coupled to each other. So this is very difficult part. For that you need the computational fluid dynamics, that is the different subject. And the computational fluid dynamics deals with the solutions of the complex fluid mechanics problem by using the different fluid mechanics softwares. Okay, so in that software, basically that software uses the equation of motion to determine the flow in the 2D and 3D dimensions when you have the turbulent flow. And even for that software, it is not easy to solve the software for large scale equipments. You can solve the equation for 1 centimeter, 2 centimeter length, but if you want to solve for the 10 meter or 15 meter distance, then the equation will not converge. And because the solution, the calculations required are very huge. You have to solve the 15 lakhs, 16 lakhs equation per second for 4 days, for many days. Then only you will get the solution of the one problem. Okay, so this much difficult is to solve these equations for the complex problems. Okay, so it is not easy to use the micro level mechanics, fluid mechanics at the large scale operation for turbulent flow. Okay, for laminar flow it is easy. But whatever the equations we solve, whatever the derivation we had done, that is only for the laminar flow. If you are solving the turbulent flow, then for each point you have the fluid may move in this direction, fluid may move in this direction, fluid may move in all three directions, and it may also depend upon time. Okay, so the solution become very typical, and you have to solve all the equation of motions with time also, and that is also the second order partial differential equations. So the solution required the huge amount of computational power. Okay, so even that software cannot be solved by simple. If you are using the computational CFD software, that is not running on that will not run on the simple computer. You need the higher processing power. Okay, so for that you can use the GPUs and high power GPUs, high processor GPUs to solve the problem, or you have to go for the supercomputers. Okay, so still with the so much advances in the computer hardware, we cannot use the micro level mechanics to solve the major big problem for the fluid mechanics. So for alternative solution, which is very easy, is the macro level fluid mechanics. So what is the macro level fluid mechanics? From the today's class, we will study only the macro level fluid mechanics, not the micro level. Okay, so in the transport phenomena, in the initial part of the fluid mechanics, we have studied the micro level fluid mechanics, where we calculate the flow at the local level. So suppose fluid is flowing from one tank to the other tank. So this is the tank number 1. And suppose this is a reactor where reaction is occurring. So this is a reactor. Okay. Now this is the reactant which will flows from this tank to this tank. Now you have to design the hydraulic system. You have to design a pump which will flow the fluid from this tank to this tank, and you have to design this pipeline. You know what should be the size of the pipeline. Okay, so the fluid can be flow from one point to the other point. Okay, these 2 points you have to design. So your basic motive is the overall flow rate. In this problem, it is not required to know the fluid flow behavior or the velocity of the fluid at a local point. Huh? You need not to worry about what is the flow of the fluid at a local point, at this point or this point or this point. Okay, that is not a major problem. The major problem is how much fluid flows within in a given time from this point to this point. Okay, so what we will do, suppose this is the pipeline. So if the fluid is flow is laminar, then you have the laminar flow velocity profile. At the middle point, velocity is maximum. At the wall, velocity is minimum. Okay, so here velocity is vzx, which will depend upon x. So what we will do, we will average out the velocity. Okay, instead of using the local velocity, we will use the average velocity. So what is the meaning of the average velocity? Average velocity means, suppose the volumetric flow of the fluid is q. Q is the like x meter cube per second. This is the volumetric flow rate of the fluid. Okay, suppose the 15 liter or the 15 meter cube of fluid is flowing from here to here per second. That is the volumetric flow rate. How much volume is transporting from one point to the other point in a given time. That is the volumetric flow rate. Divided by the cross-sectional area of the pipeline. So this is the cross-sectional area of the pipeline. This is the pipe. So this is the cross-sectional area of the pipeline. So the cross-sectional area is A. So when you divide the Q divided by A, it will become B. Okay, so I am writing in a more clear form. So X is volumetric flow rate, that is equal, also represented by Q. So now this is the volumetric flow rate. Now when you divide volumetric flow rate to the cross-sectional area, A is cross-sectional area. Of the flowing channel. Now when you divide Q by A, then you will get V average. That is equal to Q, or the X divided by, here X equal to Q, volumetric flow rate equal to X. So X divided by A, or just represent it by Q. So Q divided by A. So this is the average velocity. This is not the velocity at any point. This is the average of the all velocity. At the wall, the velocity might be 0. At the center, velocity might be the highest velocity, maximum velocity. So when you take the average, you will get this average velocity. Okay. Now instead of writing the local velocity at every point, we will use the average velocity. What is the benefit of to average out the velocity? Suppose your fluid is flowing like a turbulent fluid. So at a local point, the fluid particle, the molecule of the fluid may move in any direction. Okay, that may also depend upon the time. But when you average out, you will get a constant value, because overall fluid is flowing in a one direction. Overall fluid is flowing in this direction only. Okay, so whenever you average out the velocity, you will get a constant value. So now the uncertainty will remove. Okay, once you average out the velocity, then you can easily solve the problem. Okay, now the problem becomes very easy. Even you don't need not to use the differential calculus, differential or integral calculus. This will become simple algebraic problem. You can use the Bernoulli equation and use the friction factor parameters, and you can determine how much power is required to flow the fluid from one point to the other point. Okay, so from the next class we will solve the macro level fluid mechanics problems. Okay, we will discuss the Bernoulli equation and other basic concept. You have already studied the Bernoulli equation in the lab class, so we will discuss the Bernoulli equation in the more detailed form. Then we will solve the problem for the power requirement to transport the fluid from one point to the other point, how to design the pump, and how to calculate the pressure loss inside the pipeline. Okay? I think this is enough for today's class.
Yes, sir.
ठीक है, फिर नेक्स्ट क्लास नेक्स्ट वीक में मिलते हैं, है ना? उसमें फिर
Monday.
आगे का मंडे को। चलो ठीक है, किसी को पूछना है?
नो सर।
चलो ठीक है, समझ में आया ना आज का क्लास का?
यस सर।
चलो,
Yes,
है ना?
sir.